How's it going, everyone? Welcome to the fourth drill of the Spring 21 semester. Today we're going to be talking about what some people will call a two-way factorial ANOVA, or as I call it, a general linear model. In this case, a general linear model that happens to have multiple categorical predictors, two categorical predictors specifically. So we're going to be running tidyverse, elem support, and ggeffects libraries. You'll notice that I already have a plot1 down here, and once again, that's not a plot that you have in your environment just yet, but we'll talk about all that stuff later. So we're going to talk about a study where researchers are interested in wondering whether deep versus shallow processing has an impact on memory recall, and if there's a difference for old versus young people. So deep processing is when you encode the meaning of a word, relating it to other similar words. If I show you a picture of the word dog and say, does this belong in the sentence, the blank lives in the coral reef? You have to stop and think, well, what does dog mean? Dog is that animal that has, four legs and fur and the tail and barks and runs around the yard. What does coral reef mean? Okay, that's that, big thing out in the ocean. So no, dogs don't live there. Shallow processing is encoding like the structure or sound of the word. So if I show you the word dog and say, is this word in capital or lowercase letters? Or if I say, does this word rhyme with cat? You don't have to think about what does dog mean, what is dog, to know that dog doesn't rhyme with cat. I could give you words in a foreign language, and you may not know what obrigado means in Portuguese to know whether or not it rhymes with avocado. They sound kind of the same, even if you don't know that just means thank you. And so they have no meaning, but similar sounds. So that's what that shallow processing is, that superficial stuff about the word, and deep processing is really thinking about the meaning. So after being shown a list of words and asked questions to have them process it either deeply or shallow, they did a short filler task, and then they were asked to recall as many of the original words as possible, and that's what the dependent variable is the number of correctly recalled words. Because the authors did not read the paper that Bill suggested, they arbitrarily and foolishly dichotomized their continuous age variable into an old versus young group as the second predictor. And as Bill said, this is probably my top 3 favorite Bill quotes ever. Seriously, read about this, and if you are in a research world where people are still doing this, and then when you find people doing this, make sure that they know that they need to get some help because they are analyzing their data incorrectly, and there are better ways to analyze your data. And a link to that paper if you haven't read it. And just to make it clear, this is kind of in jest. I made up this part about them arbitrarily dichotomizing their age into old versus young. In the original Eisnick research that this data is based on, it's not the actual data. In the original research, they actually had 2 groups of people in their 20-somethings versus a group 55 to 65. So I'm not trying to discredit any researchers here. I'm just trying to hammer in a point that you should not arbitrarily create groups from continuous variables. If you have continuous variables, then analyze continuous variables. So we'll read in the data and take a glimpse, and we see that we've got 4 variables. X1 is just the participant ID, as I'm calling it. Recall is the number of correctly recalled words. Age is coded as 1 or 2 for young and old. Processing is coded as 1 or 2 for shallow and deep. If we look at our descriptives, we can see that on the average recall was 11.2 words with a min and max of 4 and 22 respectively. For age and process, we've got a min and max of 1 and 2, which tells us that nothing was miscoded. We don't have anyone coded as 22 on accident due to a typo or anything. And we see with the mean of 1.5 for each of those, we know that they must be a balanced design. So I'm going to go ahead and create our predictors for these things. And so what I want to do is I always advocate for creating factored versions and numeric versions for all of your predictors. And there's reasons for it. We'll talk more about it as we go. But in short, I'm going to use the factor function. and I'm going to factor both age and process, our original variables. I'm going to store those as, my convention is like variable.f for the factor version and variable.n for the numerically coded version, which is usually negative and positive half. Sometimes I will dummy code, but it's usually negative half, positive half. Which is the age.n and process.n. So I factor the age variable, and if I just did as factor age, then it would, because the actual things are just ones and twos, that's what it would assign as the labels, as 1 and 2. But I want to give it labels of, young and old, instead of 1 and 2. And then I take that factored version and I create a numeric version where young is positive half, old is negative half, and then the same thing for process, but deep is positive half and shallow is negative half. One quick note here. This is based on Bill's preferred coding as far as what gets coded as negative half, what gets coded as positive half. It doesn't matter in that the only difference is when you get to your regression tables, are your coefficients or t's or f's positive or negative? Is it does t equal 2.5 or negative 2.5? And so Bill likes to avoid negatives. Since I am primarily visually driven, in this case, I would probably code young as negative half, because when I think in terms of a graph and age being on the x-axis, moving left to right as we read, time moving left to right, young comes before old. So just in terms of conceptually, the way it maps in my head, I would think of young being, the negative variable. But again, it doesn't really matter. But I will end up flipping these back around when we get to the plotting stuff later on at the end of the script. So anyway, I create my variables and then just double check and see that, yep, we've created our factor versions as well as our numeric versions of each of these variables. And then we'll check how we coded that, just to make sure, by piping the variables that we created into a table. So here we can see that all 20 of the ones were coded as young, all 20 of the olds were coded as 2. Same thing for process, all of the ones were coded shallow, all the 2s were coded deep. And then if we look at the crosstabs of the factored versions that we created, we can see that there are 10 per cell as we expected. So now we'll look at some summary data real quick and just see, like, well, what is the what does the recall look like? Here, all I want to point out is that I'm going to save. I'm going to get the conditional means using the same piping that we've always used, and if I just run that subset, it'll pop up and it'll be there. But I want to store con means as an object that we'll call back. But what I want to point out is that if I have this extra set of parentheses, and so I've mentioned this before, but what I want to point out is that normally if I run just what's inside the parentheses, it will take this table and store it as an object called con means. By wrapping the whole thing in parentheses, it will store that object as con means, but it will also output or it will display that output. So when I run that, it both stores it as an object and gives me that output. So we can see, like, what our condition means are there. And then if we wanted to break it down by just age, all we got to do is take out that process from the group by, and we can see that same thing for looking at our marginal means for process, and then the overall mean. And then just a quick note, if you, for whatever reason, don't like the non-tidy way and wanted to use aggregate, Bill uses this occasionally. Here's how you could do that. I'm not going to really get into that. I just put it in there for those of you who want to see it, but I literally don't use that at all ever. As far as the plots, Bill finds this interaction plot to be an easy way to explore interactions, albeit not very visually pleasing. For the x factor, you just put in whatever the x-axis factor is. The other factor will be this trace dot factor, and then response is your dv. I also find my preferred way to be really easy, and I'd argue that it's better because it's a lot more visually pleasing, because it's in ggplot, of course. It's essentially nothing new because it's the same process we used before to do our regression lines and CIs, but instead of using ggpredict, we're going to use a function called ggem_means, which is gg estimated marginal means. And really it only has 2 steps instead of this one, but it's far more flexible because ggeffects can handle most types of models, so you're using these same basic tools and approach for all of your analyses. And what I mean by ggeffects can handle most types of models is that so far all of our models have been using LM. We've used LM models, and it's been, y regressed on X. Once we get to, mixed effects models, we'll use what are called Elmer models, and that there's additional, whatever things that you have to specify for those. There are Bayesian models. There are dozens of different types of models. And ggeffects can handle almost all of them. So this one approach of learning ggeffects means that when you move on into other things that aren't this simple, like 2x2 design, you can also use this approach with those. But I put all of that at the end. It is kind of long because I wanted to walk you all through the idea that doing nice plots is an iterative process that you just continue building and tweaking and piecing together, and that it's not something that you necessarily just sit down and write all of it out at once. But again, that's more than what Bill requires you to know. So I put it at the end so that once I get there, if you don't care, then you can turn off the video and stop reading the script, but it's there for people who want it. Here's that plot 1 that I had, which is the same thing as this. And I show how to make this plot later, but I also included the 95% confidence intervals at the ends of these lines. Because I just always want confidence intervals on my plots. But outside of that, these two are essentially the same plots. And that this, what I call plot 1, is what I think of as the minimal approximation of this interaction plot. And really it's only 2 lines. There's a geom line and then geom error bars after one GM or GGEM means code. Anyway, so we'll just leave this plot up while we work, and we're going to start by running this as an ANOVA. Now, before we run it as an ANOVA, we're going to create the model as an LM model, as we always have before. So I'm literally calling this the model, and it's just using LM, and all we're saying is recall regressed on the factorized versions of age and process, just like we've always done before. Well, here I'm specifying it's essentially the same thing, except I instead of using LM, I'm putting it in AOV. So I'm specifying the model as an ANOVA object, or as an ANOVA model, and then putting that inside summary. Whereas here I'm taking the model that we created and putting that inside AOV inside summary. And the point here is that when we run these two things, you'll see that it is the exact same output. So the point of this demonstration is that you can always specify your models with LM the way that we always have, and then put it into AOV if you are trying to do it as an ANOVA for some reason. You don't have to specify it as this ANOVA model if you want to do an ANOVA, but then change it to LM, if you want to do something as a linear model later. Like, you can just put your linear models into the ANOVA function, the AOV, and get the same thing. But anyway, so if you run your ANOVA here, you would see, yep, there is a significant effect of age, a significant effect of process, and a significant interaction of the two. I don't really care to get any more into interpretations or anything like that of the ANOVA portion. Instead, what I will do is we're going to jump right into the linear modeling and look at how that compares to this ANOVA. So since the model uses the factored version of age and process that we created, let's look at the coding first just to see how it's coded, how these contrasts are coded. And like, as a reminder, it's dummy coded. It's always just dummy coded by default. So what does it mean interpretively for us with these things being dummy coded then? Well, so we're going to look at the model summary of the model, and keep in mind that this is the same model as we have here in our ANOVA, only we're just not running it through the ANOVA function. We're just putting it straight into summary. Well, and we could just use the base R summary. Again, I like to use model summary you can because you can select it to report F's instead of T's. So that's all we're doing here. So also I'm going to pull up the condition means to remind ourselves of that. And like now let's take a look at this and figure out what all this means. So how do you interpret literally all regressions? The intercept is what? It is the mean, the average predicted score when all of the predictors are 0. Well, where are all of the predictors 0? All of the predictors are 0 when it is young and shallow. And then as far as the interaction, that would be both young and shallow. And so, in other words, this intercept 6.5 is the average recall for the young shallow group. And if we look at our condition means, we see 6.5 is the average recall for the young shallow group. The slope of age is 0.5. That tells us that if you set everything to 0 so that we get that intercept of 6.5, a 1 unit increase in age, which means the old group instead of the young group, is associated with that intercept increasing by half a point. So in other words, that old group still holding the processing at shallow, that old group should have a mean of 7. And when we look at the old shallow group, sure enough, that mean is 7. Then for the slope of process, what this means is holding everything else at 0, where we have that intercept at 6.5, a 1 unit increase in processing from shallow to deep is associated with increasing that intercept by 12.8 points. And so when we look at our young deep group, that's exactly what we see. We see the mean of 19.3. Now the interactions, especially in this particular case, when things are dummy coded like this can be kind of difficult for some people to wrap their heads around. But if you stop and remember that when you see an interaction in a regression model, all that slope is telling you is it's a difference of differences. And so if the age, if this parameter is a 1 unit increase, the slope that's associated with a 1 unit increase in age. This one down here says if you flip either x1 or x2 up 1 point, then this slope is the predicted change in the slope of x2. So in other words, whereas this intercept is the young shallow group, this is the slope for age for the slope for process. The slope of this interaction means if you switch to the old group, switch to 1, then what is the change in slope of process? So because of that, if 6.5 is our young shallow, and if we increase to old, then that's expected to go up by 0.5 point. But then the slope of process is going to go down by 7.8. So whereas it was 12.8 for the young group, for the old group, it's 12.8 minus 7.8. So that's a difference of 5. So that would mean that the slope of process for the old people would be 5. Well, so if we have an intercept of 6.5 plus for old people, that expectation is going to go up by 0.5 point. Plus, now our slope of process is 5, because again, it's 12.8 minus 7.8. So now we get that old deep processing has a mean of 12. So again, like the reason that this interaction when you're dummy coding can be hard for some people to interpret is because you have to remember that this changes the slope of one of these two things, and it could go either way. We could have gone the other way and said, 1/2 minus 7.8, and then said that, well, the intercept is 6.5. For the deep processing, we need to add 12.8. And then we also need to add the slope, but if we are in the deep processing, then the interaction means that here we need 7.8 less than the current slope. We're saying that we will reduce the age of slope by 7.8. So we do 0.5 minus 7.8 here. Again, we get the same thing. So the interactions go either way. You can think of it as, well, if you switch this factor to level 1 instead of level 0, then the interaction slope is how much you increase or decrease the slope of x2 by. Or if you increase x2 by 1 point, then the interaction is how much you increase or decrease the slope of x1 by. But either way, you come up with that 12 for the average. So how does that then compare with our ANOVA from before? Again, here we're looking at, it's the same model. Here is just a model summary of the model, and here is the summary of the model as an AOV. But you notice that things don't line up. Our F here for age is 0.18, and here it's 17.44. For process, it's 123 versus 119. And then, the interaction is pretty close, 22.95, so at least we got that one thing. But what's going on here, and why don't these things line up? Well, let's fit our model with the orthogonal, negative half, positive half coded contrasts. So it's the exact same model, just switching age F and process F to age and process N. And now let's look at our model summary again. And the first thing that I'll actually point out is looking at how does this compare to the ANOVA table, and we see that now our ANOVAs line up. Our age, the F of the regression is 17.44, and on the ANOVA table it's 17.44. For process, the F is 119.51, and then again 22.95 for the interactions. So now that we have orthogonally coded predictors, our linear regression literally gives us the exact same results as the ANOVA does. So how does the interpretations differ from from this compared to our dummy coded model. So if this one down at the bottom is dummy coded, remember that 6.5 was the mean for the group that was coded 0. Well, here, if everything is coded as -½ and +½ then this 11.2 will be the overall mean. Which we see. The slope of, let's run back and pull up the, so 11.2 is that overall mean. The slope of age of 3.4 is now going to tell you the difference between the two groups as a function of age. So if we look here, we see that 12.9 minus 9.5, we get 3.4 right there. For process, the slope of 8.9 tells us that the difference between our processing groups, 15.6 minus 6.75, is 8.85, which didn't line up there exactly. Oh, rounding errors, because this is rounded down to only 3. That's why. So that's actually, keep in mind, with these tibbles, they by default only print out those 3 significant digits. So if instead we ran it as a data frame, we could now see it's 15.65 minus 6.75, which is where we get that 8.9. So that's why, like I said, that the slope of process is the difference between those two groups. So do keep rounding errors in mind whenever you're trying to check these things. And then finally, that interaction between age and process. And so again, it's the interaction is the difference of differences. So a 1 unit increase in one of these 2 variables is associated with a change of how much of the other slope. And that's exactly what we're seeing here. So then you would, as you can see, all 3 of these things are significant, just like that original ANOVA. And then so we see that like these contrast, these orthogonally contrast coded, variables, dichotomous variables, works out to be the exact same as that ANOVA. So then the question becomes about testing simple effects. So we can say, yes, there are significant differences here amongst these data. But simple effects asks for like, what is the effect of x1 for a specific or each level of x2 or vice versa. So what is the simple slope? What is the effect of processing for young people? So that would be asking like, well, what's the difference between this thing and this thing? The simple effect of processing for old people would be the difference between this and this. The simple effect of age for group for processing, deep processing, would be, well, like the slope of this line, what's the difference between this group and this group? And then the simple slope or simple effect of processing for the shallow condition would be the difference between this one and this one. So in other words, the slope of this line. So in order to test simple effects, we're going to create manual dummy codes for each of these variables. And we'll call it age young dummy, age old dummy, process shallow dummy, process deep dummy. And all it is that for the age young dummy, like anything that is young, we code as 0. Anything that's old, we code as 1. For age old dummy, we do the opposite. And then same process for shallow and deep dummy codes. So we'll run that line, and then we will check just to make sure. And all of our young people are coded as 0 for the young dummies, 1s for the old dummies, and then shallows are coded 0s for the shallow dummies and 1s for the deep dummies. Once again, we'll just remind ourselves of those condition means. And now let's look at the simple slopes. So the simple slope of, or simple effect of age for deep processing, we're going to create a model where we recall on age and interacting with that process deep dummy. So when we do that, now we're looking at the simple slopes of age for, again, this is because we have the deep dummy, which means people coded as deep are 0 and people coded as shallow are 1. Then this means that the slope for people who are in that deep processing condition, in other words, this line here, their slope for age is 7.3. For shallow processing, the simple slope of age is not significant, whereas it is significant here. Obviously, that's a very sharp, and you can see that the confidence intervals of this group do not overlap with the confidence intervals of this group, which tells you that this line is significant. Here for the shallow group, that slope is not significant. And you may be wondering, why is it that this says 7.3 is the slope, and I'm saying that that's this line right here, and then this one says -0.5, and I'm saying that's this line. Well, that's because this graph is actually flipped around backwards. Like I said, young is actually coded as +0.5 and old is coded as -0.5. And so the real image here would be flipped around the other way. So that's where I talked about just flipping those signs. If we coded this around the other way and coded young as -0.5 and old as +0.5, then this would be +0.5 and this would be -7.3. But notice how the process deep dummy and the interaction parameters, like they don't change their predictions any. The intercept and slope of age does, but these two don't. It just flips those signs between the two. So when you stop to consider what these different things mean in the context of how do you interpret a regression table. Again, if our intercept is the predicted score when everything is 0, that means that the intercept is going to be here, where we'll look at first our deep dummies. The intercept is going to be like all the deep processing, this blue line, all of these people are coded as 0. So the intercept is the average for all of those people 15.65, which is what we see. The slope of age is what is the slope of this blue line, or what is the difference between the age groups. This negative 8.9 will be if you change process deep dummy from 0 to 1, meaning switching to all of these red guys down here, it's going to drop that estimate by this one by 8.9. And then again, the interactions can kind of be difficult for some people to interpret initially, which is, okay, if we go up 1 unit in age, say from young to old, what does the slope of x2 do? Does it go up or down, and by how much? Or you can say that the other way. If we bump x2 up by 1, so if we make this we go up by 1 on process deep dummy, which means we're now looking at the shallow group people, how does the slope of age change? And well, the answer is it would become negative 1/2, which is coincidentally exactly what we see when we flip that around. That now when we do process shallow dummy, we're looking at the intercept is our mean of the shallow group. That slope of age is negative 1/2. And then again, if we switch that process shallow dummy to 1, then we're back to talking about the deep group. So we add 8.9 to that intercept. And then as far as the interaction, if we switch this to 1, that means that we're going to add 8.9 to that for being the other group. And then the slope of the other predictor will change by 7.8, meaning that becomes the same 7.3 that you see here. Same thing for looking at the simple slopes of our others. So if we want to see the simple slope of processing for young people, we see that is significant. So this is the age young dummy. So here, this group over here on the left is coded as 0. So the intercept is going to be the average of that. And so now let's go back up and check our means by age. And so that 12.9 is the mean of young people, just as we see here. The effect of process, a 1 unit increase in process, or the difference between process between deep and shallow, the average difference between those two is going to be 12.8. And then again, a 1 unit increase in age young dummy, which means looking at the old people, will decrease that parameter, that intercept by 3.4, which we see here. You subtract 3.4 from 12.9, you get 9.5. And then again, the interaction is if you go up 1 unit in, I think it's easier to think of it this way, a 1 unit increase in age young dummy. So once you are looking at the old people, what happens to the slope of process? Well, it goes down by 12.8. So this should become 12.8 minus 7.8, or 5. So this interaction tells us that the slope for age old dummy should be 5. And if we take a look down here, we see that that's what we get. We now have our mean for age old dummy. So now we're looking at this group over here is coded as 0, and this group over here is coded as 1. So the intercept being the average where things are 0 means the average for this group over here, 9.5. And also keep in mind that because process is coded as negative half, positive half, that means that it's collapsed across groups, which is why now that we're using process in, we're saying that this is the difference between group A and group B, rather than this is the predicted change for the group coded as 0. There is no group coded as 0 as far as the process, just for the dummy codes of age. So hopefully by now I don't need to beat that horse anymore, and you can pick up what we're putting down as far as how to interpret those. Although if you have any questions or I need to explain it in any more depth, do let me know. So that's basically it as far as the drill video today. If you have no interest in hearing about ggplot and things, you can go ahead and turn off the video. You can stop working here in the script. From here to the bottom is all just extra stuff to show you some tricks for ggplot. So the first thing I want to show the plot that we had above. That was the one that Bill had. And here below is my easy way, meaning the minimal amount of code to approximate this interaction plot. And we've used ggpredict before to plot regression lines and CIs, and there's another thing called ggEM_means, which is just the GG estimated marginal means. And this works just like ggpredict, only it gives you the estimated marginal means of things. And so if I run this just into Glimpse, just so that you can see what the actual table outputs, when you run ggmeans, it produces this tibble that'll give you something called X, which is young, old, old. It's a factor. Predicted, that'll be those actual marginal means, the 6.5, 19.3, 7, and 12. That should look familiar. Where if we scroll up and look at our con means, the standard error, confidence intervals, and then group being shallow versus deep. So this just puts out this 4 by 6 tibble. We're going to pipe that straight into ggplot, and the entire plot that I made, like if we just run this first part with the geom line, like there is, the same plot as so really with just that one, you can leave off the theme classic if you want. I like it, and that's just my default, because I don't like the gray background that comes in the default. So I like to put theme classic, but you could leave that off. But my point is basically that there's 2 lines, ggEM_means, and then all you're having to do is plot one geom line to get that same plot as this one. Only, even that I think looks nicer. But then I also add the error bar with geom error bar, which is how all I did. I'm telling it that I want x to equal x, which is the young versus old factor. Y min is conf flow, y max is conf high, and then you have to tell it to group it by this group as either deep or shallow, and then color it by that. The width just adjusts how wide these bars are, and so that's simple and straightforward, and that is the plot one that I made before things started. That is the most simple, straightforward, direct way of doing this. But if I were going to go all out, if I was trying to make a pretty plot because it's either for a publication or a conference poster or something like that, I would definitely do a lot more with this. And so below I want to talk about kind of what exactly I might do. It's going to look like there's a lot, but really I'm walking you through a process. It's not specific things that you have to memorize. I'm just trying to demonstrate the process. There's a lot of pre and mid processing parts, transforming variables, gathering means, things like that you're going to see the whole process. And the idea is that you start out with an idea of what you want, and you start piecing it together a bit by bit and polishing things and making adjustments along the way. And it seems like this is a lot, but it seems like it's a lot because I manually do almost everything. Because once you understand how it works that way, it makes it really easy to adapt it to whatever your design and analysis is. Especially since, like I said, ggeffects can handle non-LM objects. So the first thing I'm going to do is I'm going to use GGEM means, and I'm actually going to use the model contrast, so the numeric version. So I'm going to tell it that my terms are age in and process in, and so once again, here is what it outputs, or if you want to see it in this form, like there it is. So the first things as far as pre-processing that I want to do is I want to recode age to make it to where young is to the left of old. Just because here, like as it happens to be, right now old is coded as -½ and young is coded as +½ which means that this is flipped around. So Bill likes it that way, like I said, just because he likes avoiding those negatives in the tables. But me, like intuitively, I want young to be on the left of old. If we look at our levels for group, which is supposed to be that processing condition, it's -½ then +½ but I actually want to flip that around. I want to reverse the levels. And the long story short is because it's in this legend, it automatically puts your factors in factor order. And since shallow is coded as -½ it puts that one first. And I just like the idea of deep being on top of shallow, since in the plot, like the blue line is on top of the pink line here. So I'm going to flip that around too. So all I'm going to do is take that plot df that I created, this GGEM means, and I'm going to multiply x by -1 to flip that sign. And then I'm going to factor group, and I'm going to tell it that the levels to reverse the levels. REV is just the reverse. And so that says to reverse the levels of that factor and recreate that factor called condition. So run that, and now if we check our plot df, we now have age has been flipped around, and condition has also, and condition is rather under the hood. Those levels are switched around. So then we start by basically making that same plot that we made before. I'm going to call it plot 2.0 now. But this is essentially the same as the previous plot. You can see that there are a few differences. One, that this one, the original one, was made with that factorized version. This one was made with the numeric version. The reason I like using the numeric version for plots in particular is because it makes it really easy to adjust all your margins and such. This is at -½ this is at +½ so if you're wanting to create extra space on the left and right, you just need to adjust your margin, and like that's what you'll see we do here. So from here I make this first plot, and then I start by making small adjustments. So I'm just going to take this highlight to run chunks at a time. The first thing I'm going to do is I'm going to adjust my x-axis. So first I give it a title of age, and then well, actually let's start by running plot 2.0 and then just with this one additional level added in, or this one additional line. So you can see what I've done is the limits is how far out the x and y axis go. So they go from -0.75 to 0.75. So I switched this to bring these in a little bit and have this x-axis start over here and this one go out a little further. Breaks are where these tick marks are. So in this picture, there's a break at -0.6, -0.3, 0, 0.3, and 0.6. But by telling it I only want breaks at -½ and +½ that means that it only has the tick marks and labels at old and young. So even though like this is actually 0 and that this is all numeric, I only have those tick marks and labels at those two specific points. And then the labels for those two specific tick marks are old and young. I want to do. I want to also adjust the colors because I don't like this, kind of aqua and salmon default colors. So first, I'm going to capitalize condition here, just because it should be. And then I'm going to tell it, like, I want the color, the values, I want the values to be red and blue, and the labels, instead of being, 0.5 and negative 0.5, will be deep and shallow. So when I run that chunk, that's exactly what we get. So now we've changed that next little piece. Also, I want to, well, every plot should have a title. And I don't want this just to be predicted. I want a useful label over here on the y-axis. And plus, I'll add a caption down at the bottom. Now, in this caption, you'll notice several things. First, it is like right justified over here. I have this string wrap function. Basically, what this does is if I take out the string wrap and I just have this one line, and I rerun this plot without that string wrap, it will just put everything on one line, and again, it will right justify it. String wrap is a convenient stringer, whatever you want to call it, function that essentially takes whatever you put in and will automatically apply some wrapping to it. So that's how I get it to break that line at its margin and all fit onto one thing. And as we go on, this will make some more sense, because of course that's still ugly and terrible. But there are clearly some more adjustments that need to be made. So from here, I would make some manual theme adjustments. Legend position, what this is going to do is tell it to take this legend and move it onto the plot. The plot space is this line right here, where that line ends, and which is where also you notice the caption only goes to that margin. So this whole area over here is just marginal white space. It's awful when we have all of this space over here. So you could move the legend either up here, or you could put it here in all this empty space. We're going to move it up here, which is, we're going to say, is 80% to the right and 80% up. Legend box background, all this is going to do is element rectangle, is I want to put a border around this. In fact, I'm just going to go ahead and run this whole chunk and then show you what the plot looks like so you can see. So now it's the difference in this versus this is just adding the this theme line. So again, this legend box background element rectangle puts this box around it. If you wanted to change like colors of that, you could do that in here, or fills, etc. Plot title, element text H just, that's the horizontal justification. 0.5 means to center it, because I want to center that title. The plot caption, if you recall, before it was left justified, and I obviously want that caption to be right justified. So plot caption, we'll say element text H just equals 0, because it's a 0 to 1. And then finally, for the text, like I just want to change all of the text on the plot to Times New Roman, with the base size being size 12. And it'll still adjust, text to be appropriately bigger or smaller. It won't just make everything size 12. That's the base size. So if we run this, I'm going to come back now and take off this so that we can run it and save that as plot 2.1. So now we have a nicer plot, be sure, but I really prefer to show my raw data alongside the models, and I always advocate for doing the same when at all possible. There are times, such as in logistic regression or in other forms of modeling where you literally transform the data in a way that the raw data are no longer a thing. Like you can't visualize the raw data with the model. You have to do it separately. But that's not the case here. So looking back at what at the raw data, what I want to do is, since age is coded as 1 and 2, I'm going to recode that, and I'm going to make age, I'm going to subtract 1.5 from age. So what that's going to do, if you subtract 1.5 from 1, obviously you get -1/2, and you subtract 1.5 from 2, you get +1/2. So I'm basically recoding the age variable here to be plus and minus 1/2 as age.n is. For condition, I'm also reversing those levels just as I did before. So basically, so that my raw data here in a data set that I'm calling plot df2 now has those 2 additional variables and recoded the age variable for me. So now using this, what I'm calling plot df2, I will add the raw data onto this plot 2.1, which is what I stored here. So I'm going to set a seed, 42 in this case. And just to be clear, these set seeds, it is a one-time thing. Anytime you have any process that involves randomness, it has some seed that it uses to generate that randomness. Well, the only way to repeat a random process is to set a seed for it each and every time. So here, since we have geom jitter, it will randomly move things to the left and right. Every time you run something with randomness, it will give you different randomness. So the point is that just 37, you've seen pop up several times. That's kind of like my starting point. And I literally, what I did here was I set the seed on something. Like here, I'll just demonstrate by running this plot. So if we run this, 3-4 times, and then click back through the plots, you can see that each time it gives us a different plot because it's randomly moving those things around. But if each time we run a seed, now we can see that even though I'm clicking these different plots, it's giving us the same thing. So again, don't think that there's anything special about this seed. I started at 37. And it had some overlap that I didn't like in a couple of the dots. And so I changed it to seed 38 and ran that, and then 39. And I kept going until I got to 42, finally got to one that wasn't overlapping, too many data points in a way that I didn't like. So that's how I settled on seed 42. But literally, it doesn't matter what you pick. The purpose of using the seed is so that you can reproduce the exact same plot each time. Anyway, so I'm taking plot 2.1, the plot that we made before, and all I'm doing is I'm adding another layer, a geom jitter, but I'm telling it that the data is now plot df2 that we created here. And I want to tell it that for the geom jitter, the width is 0.1 to let it move side to side. Height is 0 because I want to maintain fidelity of the y-axis. I don't want it to randomly jitter things higher or lower, just to the left or right so that they don't overlap. And in fact, we can take a look at what it looks like if you don't jitter. If we set the width to 0, you can see it just keeps everything so you have overlapping dots. For the shape, we changed it to filled circle. Now, whenever you're using these filled circles, the fill is the color on the inside, and color is what color is the outline. So alpha being 0.4 just makes it to where if there's overlap, it there's transparency, so you can see it. And then finally, I'm going to add scale fill manual. So this is similar to the scale color manual that I used. In fact, if you notice, if we copy and paste that down here so that we can compare these, you'll notice that the title is exactly the same, condition with that capital C, and that my labels, deep and shallow, are the same. And it doesn't matter that I'm making the colors the same, even though they are. What is important is that because the label, the title of that is the same, and the labels are the same, it will, our ggplot will combine the fill legend with that color legend. So in other words, you see over here how right now, because I just ran this section here and I haven't run that manual fill yet, it's giving me the default salmon and aqua colors for that fill argument. But once I add on this, because the label is the same, the labels are the same, and that title is the same, then what it will do is it will combine those. So instead of giving me one legend for the lines and one legend for the dots, it combines them together. It recognizes that, oh, this is the same thing because it has the same title and the same labels. So that's the reason I like the manual things. I like manually controlling all of my stuff. To me, it's just, it's not that hard. It has a lot of nice features about it, and it makes it to where it's always the same approach. So now I'm going to store that as, so this plot here now, we'll store that as plot 2.2. And so like that could be fine. Actually, I need to go back and run my seed before I run it. So that way we all have the same plot. So, this could fly as this. I'd put this on a poster or, a publication, whatever. The final thing that I might add are the mean and CI bars for the marginal means, like the conditional means. And so what I would do is put like the mean and confidence interval for the deep condition here, like in the middle, and the mean and confidence interval for the shallow condition here in the middle. And so the way that I would do that is start with taking that DF2 data frame that we created and redoing the recall regressed on age by condition. So switching to those the numerically coded version of these. But this time for GGEM means, instead of doing both age and condition, we just want the means and CIs for condition. We don't want it broken down by both. So all I'm doing with that is I'm taking the GGEM means, I'm piping it into Tibble so that it outputs it changes it to a Tibble. And then I'm mutating just to change the names of things. I'm going to create a variable called condition, which is this X variable, factor versus shallow. And recall is going to be this predicted variable. And so now when I look at plot DF3, here's what we have. So now I take plot 2.2 that we already have here, and I add on a layer, and I tell it that plot DF3, a geome point, and I'm just going to tell it that x equals 0, because again, even though this doesn't look like a numeric axis, it actually is. It's just labeled young and old instead of negative half and positive half, but we know 0 is right here in the middle, and y equals recall. So now we have the means plotted for the deep and shallow conditions respectively. Geom error bar, same thing. Pull it from the DF. X is 0, and only now we're going to tell it conf low and conf high for Y min and Y max. And so then that would put our CIs there. And then the final thing is, that you might need to adjust your caption here because it is a little bit different. And so, things are looking good now. So now we could have this finalized thing called color plot. And here is like the final plot. This is this is what, put in the publication, put in your poster. One last thing though that I want to point out is like sometimes it is important to think in black and white, literally speaking. Some journals require black and white plots. Others say like black and white plots strongly preferred. If you absolutely have to use color to be able to visualize whatever it is that you're trying to show, if you can justify it to the editors, like we'll approve color on a case-by-case basis. But in general, like we require black and white prints. Or in terms of like if you're printing posters for a conference, sometimes depending on what route you're going, getting color is like many times more expensive than doing black and white. So you might want to make things black and white. And so it's important to think about how can you visualize data when you can't use color. So this code below, all I've done is I've taken all of this code above and kind of crunched it into one chunk of code, and I've annotated where things are different. So again, I'm going to set the seed to 42 because that's the same seed I used before, so that I'll get the same jitter on these. But then as far as the plot, like this is again starting like start to finish, all just one chunk of code here. And so everything starts out the same except color here in the original geom line has been changed to line type so that I can use different line types instead of different colors. So then we add on our error bars. We adjust our x-axis, scale line type. Instead of scale color manual, it's scale line type manual. And the only thing that I'm doing is instead of it being blue and red, I'm telling it I want shallow or solid and dashed lines. You could do dotted instead of dashed. There are different types of lines. I like dashed more than dotted. So then, here we we add our labels now, because we want to add a title and an informative y-axis. Make the adjustments on the theme. Which, as before, that is simply moving the legend onto the plot to get rid of all that white space on the edge, putting the box around the legend, centering the title, left justifying the caption, and then changing all the font to Times New Roman with a base size of 12. Here, I just got rid of the alpha to make all of the points opaque. As a reminder, I added this color equals black because that will add the outline you notice is black on all these. They're either these aqua with black circles or salmon with black circles. And so fill is that salmon versus aqua. Black is the circle around it. So what that means is now whenever I do a scale fill manual, instead of it being red and blue, I'm changing it to black and white. But because I said that color equals black, that means that these are like white dots that are surrounded by black. Finally, moving on to the last bit of this, I have changed this geom point for the means to squares, filled squares, instead of before they were just the regular points. But now that I have black dots on the page, I don't want the dots in here that might in any way be confused. So it just makes it more clear that this is separate from these over here because they're the squares. Add the error bars just as before. And then finally add our caption. And when we delete this to run the whole thing by setting the seed first, and now we have our final thing called poster plot, that we have the same thing as color plot, only it's in a version that's in black and white instead of in color. So being able to play with, and you could use different types of grays depending on the data. Sometimes you use shapes to make these differences. So I just wanted to get you thinking about the times when you have to get creative with how to display data when you can't use color. Anyway, that wraps up this drill video. If you have any questions, as always, just let me know.